All right, folks, back to games with a double slit. Just previously, we found out how to find the interfringe distance from a double slit apparatus, and that's a cool game to play. Another cool game we like to play is, let's say that we insert, and there is a limit on how thick this thing can be. Let's say we insert a piece of mica or whatever glass here, okay? And what impact will that have? Let's say that this mica has thickness T and index of refraction N. I'd like you to pause this video and reformulate your expression for path difference. Given that these two sources still start in phase, what other games can we play? Guys, we can put the source here a little bit above, right now it's sitting right at the midpoint, right here. We can make this source, a little bit above or below the midpoint. This is not exactly the midpoint here, right? So make that midpoint, right? So now more or less this is equal to that. That's where we want to be. And this source should have been up a little bit, but that's fine. So basically, the source now is here. Like we assumed it was in the middle of the two, right? Let's say that the source is, moved, we move the source up a little bit from here. We can play that kind of game as well by changing the total path, that these two rays travel, right? Again, everything here is measured from the center, right? So let's play the game now of putting a piece of mica or whatever, to cover one of the slits. We call it covering one of the slits. Okay, that has index of refraction N and thickness T. And what I'd like to see now is what would it do to the interference profile. Okay, guys, you think about that for a second. Pause this video and see if you can figure out how to put that into your formula somehow. Okay. So basically, guys, the idea is, again, this business of path difference. So when it comes to light, we have this now. This is going to muck things up a little bit, right? Because it's an optical device. It's got an index of refraction. It's going to affect things. Light traveling through a medium of index of refraction N thinks that it's traveling a distance of N times whatever the thickness is. Remember, we said that we have light traveling through vacuum. It covers a distance D, okay, and light going through, some sort of object of thickness D and index of refraction N. The optical path here, D optical, is simply equal to D. D optical here is equal to N times D. So what I'm trying to get through to us now, for us to think about, is that if this goes through, if this covers N times D and that covers D, so this light going through a vacuum covers D, this light going through this index of refraction covers N times D. What is the amount, the extra distance that this light goes through here as compared to that distance? So how much, so this guy covers ND, this guy covers D, so what is the extra amount of distance this guy had to go through here, if it went through here, as opposed to the vacuum, okay? And that extra distance is what? Equal to D optical 1 is equal to that, D optical 2 is that, D optical 2 minus D optical 1 is equal to ND minus D is equal to D into N minus 1. That's an important result to remember for this case here, okay? So in this case, we are putting, again, a piece of whatever, glass or mica in here. What is this effectively doing is increasing the path through which this light goes. Remember the first exercise we had a few videos ago? If you change, if this was going through, let's say, without this, it went through 2 wavelengths. You put that in there, it goes through 3 wavelengths. So that's an extra wavelength that it went through. Because light travels, the distance that light travels is measured in terms of the time that it takes to travel it, or in terms of the amount of the number of wavelengths that it goes through to get through from one side to the other. So, okay, we want to see how that affects our interference. So what do we say? We say, well, look at this, guys. We say that now we have an optical thing in here. We don't just look at delta X. We have to look at something we call delta X optical. That's the optical path length. What is that equal to? What is equal to P2 optical minus P1 optical. Okay. What is P2 optical? Just like here. D1 optical is just D. P2 optical is this is just P2. That is equal to P2 minus now P1 optical is what? P1 optical is P1 geometrical. So this is geometrical equal to optical. And this is optical equal to geometrical plus something else plus that. So plus T, the thickness T into N minus 1. And that is the extra distance that the light has to go through as a result. So we're saying that it's equal to the whole P1 here, plus, so the extra distance that light has to go through as a result of this, which is equal to T into N minus 1. So now your delta X optical is equal to P2 minus P1 minus T into N minus 1, okay? And we're back to where we started in that what? P2 minus P1, this is the geometrical path, and now we find that out by dropping this down, that's equal to D sine theta. So that becomes what? Delta X optical becomes equal to D sine theta minus T into N minus 1. T is the thickness of the piece of glass and is index of refraction. And when that is equal to m lambda, we have constructive interference. And when that is equal to m plus a half lambda, we have destructive interference. Okay? So a question we always like to ask is the following. So one more time, guys. What we have done is say, because we have something happening optically, we're no longer going to just ask for the geometrical path, because light sees things differently than we do. Right? When it goes through something of medium index of refraction, so medium index of refraction n, it thinks that it covered nt instead of t. Right? So we need to start thinking optically, like light. Delta X optical is P2 optical minus P1 optical, and we recover this thing here, okay? Because now P1 optical is P1 geometrical plus the extra distance light has to go through. From there, that's just T into N minus 1. And we recognize that P2 geometrical minus P1 geometrical is just D sine theta. And we have the following result. That tells us now there is a modified formula for the position of the mth maximum or minimum. On the screen, what we usually like to look for now, guys, is what happened to the central, before we put this in, the main maximum here, where the two paths are equal, is something we call the central maximum. Okay? So if we have inserted this mica in here, the question we'd like to ask is, okay, what is the effect of that on the pattern on the screen? And the effect is that it will, okay, well, you see that it has lengthened this path here, right? So this will slow down, light will slow down a little bit, and by the time it's, by the time it exited here, that guy is there. So the distance to the central maximum is no longer going to, the central maximum is no longer going to be here. It's going to shift up a little bit. And how much it shifts up by? Well, how do you get that? You set, if you want to look for the central maximum now, say central maximum, what happened to this guy? Central maximum is at m equals 0. So you set m to be equal to 0, right? And so that's what delta x, the actual path, optical path between these two guys is 0. This happens where d sine theta minus t into n minus 1 is equal to 0, right? And that gives you, and that sine theta is 0, and that gives you the angular position of the central maximum now as what? Sine theta 0 is equal to t into n minus 1 divided by d. Okay? So this is the result. I'll write it here again. Sine theta sub 0 is equal to t into n minus 1 divided by d. Okay? And we've gotten the, so what is this telling you basically is that your central maximum, which used to be at theta equals 0, is now sitting at a different angle given by the following. There is a limit on this, of course, okay? you can tell what the limit is because, you know, we're limited by the sign. All right, folks, this is the last game. With one more game you can play. Again, when I drew this, this was not kind of lined up with the center, but everything is measured from the center. Keep that in mind. Right? We're doing things from the main axis here. It looked a bit different because, you know, it's 100%. But all these measurements are made from the central point here, from the midpoint. So, folks, this is the last game we're going to play. You can play another game on your own by allowing the source to go up a little bit distance here and see how that affects the total path difference. I'll leave that up to you. I will not be doing this part. And we're going to pause here again and get into another kind of beam splitting. We have split the beam here by using a double slit apparatus, which ensured that the beam was split up equally between two parts that are coherent. We need to do that with other devices and go into thin films and wedges. And we're going to finish this interference part by talking about the Michelson interferometer.